Alright, welcome to the BeadBuddy tutorial. So first thing you want to do is download or clone the repository from our GitHub. Here you can just download it as a zip. If that's easier, we also have a demo project available for you on Zenodo. And it's just called BB Demo for Pub. Just download that as a zip file. It might take a little second, but not too long. Then you're going to want to open MATLAB. Let's see, when you download those zips, you have to unzip them and you can put them in whatever directory you want, but you're going to have a BeadBuddy main that's coming from the GitHub, and then this demo dataset right here, which contains a few bead images, which will be our example bead images used to correct some data, and some example data right here called mydata.csv. So let's get started. In MATLAB, the first thing you want to do is go to this file browser, navigate to that BeadBuddy main folder, the one you just got off the GitHub, and that's all you need to do. Just setting the working directory, and then in the command window, you can type in BeadBuddy main, tab to autocomplete, and run the code. It'll open up the GUI. So this is the GUI for BeadBuddy. Got 3 panels. You can hover over things if you need a reminder, or I tried to put some useful tips in there to in case you forget something, to make it easier. So the first thing you need to do is select a project folder. The project folder is basically a folder that is going to contain your data that you're going to correct, as well as a subfolder that contains bead images that will build your model for correcting your data. So we're going to navigate to that demo project folder. So that's this one right here. Double click to open it, and then from here I just hit open, and you should see the file path load in here. Next, you want to type in your the dimensions of your voxel or your pixels, depending if it's 3D or 2D. If your input data set is already in units of nanometers, you can just leave these as 1. So mine is in pixel units, so I'm going to put in my XY dimension, my Z step. And then if this is a 2D data set, you can just leave the voxel the Z dimension as 1. It'll ignore it. This checkbox here, run air localize. Air localize is a script we use to do our subpixel localization of the spots. If this is the first time you're analyzing this project or these beads, then you just keep it checked. So this is just localizing the beads. And then, and if you're revisiting the project, you don't need to, if you've already done this, built the model, you don't need to check this box. Down here, third panel, so this is basically indicating whether or not you have a data set of single molecule coordinates that you want to correct. If you're just trying to analyze sort of the chromatic aberrations present in your imaging system, you can just have beads in that project folder and uncheck this and hit go. But here we have that example single molecule data set. So back in the demo data set, we've got this mydata.csv. I'm just going to open it. You can see it load the file path. Gives you a reminder of what the columns have to be, channel XYZ or XY, and then FOV, field of view, and then hit done. Next step in the GUI requires a little bit of thinking the first time you do it, but basically we're creating a table that matches the channels from your beads to the channels in your single molecule data set. So the match channel number in all the hyperstacks, or in your hyperstacks, that just basically means, what's the max numerical value of a channel used in your data set. So this is only really something to think about if you say have like a 10 channel data set, but 3 of those channels are like cytoplasmic stains or nuclear stains that you don't actually care about for localization. But for this case, it's very simple. I have 4 channels of single molecule data that I want to correct, and then I have 4 channels in my bead data set, because you need one channel, or you need 1-to-1, every channel you want to correct, you need to have beads imaged in that channel. So generate my table, and this is going to pop up. So you can go ahead and give yourself some names to keep things simple. So I'm going to say demo 637, demo, actually, this one should be 594, and so on. And then this next column is localizable. So that's kind of what I was getting at before. If one of these was, if you had a DAPI channel that was channel 1 in your single molecule data set, you would say this is 0, this is DAPI, don't try to correct this. But in our case, everything is localizable, so everyone gets a 1. Is reference, you need to choose a channel as your reference channel. Basically, all non-reference channels will be mapped or registered to this reference channel. It's a little bit arbitrary, but you can use either your densest or your best signal-to-noise ratio channel. Here I'm going to use the 637 laser line channel. Now, SMLM channel, this is your single molecule data set. These are the channel values, numerical channel values you use in your data. So for me, I have channel 1 is my Sci5 or my 637 laser line, 2, 3, 4, etc. And then in my bead channels, you can see here that it's offset by 1 with starting at 0. This is kind of what it would look like if you had a DAPI in channel 1. But here, channel 1 of my beads is also 637 laser line. And so I just have this 1-to-1, my channels are numerically all lined up. But if they don't, that's when this table comes in handy, because you need to map, say if you have, channel 2 in your data set is Sci3, but that's, channel 4 in your beads, then you would put a 4 in this column next to the 3 or whatever in your single molecule data. So just make sure that's lined up, or else you're going to get an error. And I try to put some helpful error messages in there for you. Okay, save my table. And now you're going to see it just start getting to work. It's splitting up those bead hyperstacks by channel, saving them as split channels. So for whatever reason you want to go back and look at them, you can. And then this is one of the longer step in the process, where we're just loading every single bead image and finding an optimal threshold to use for localization. And this is all sort of happening in an automated fashion. Ideally you would have more than just 3 bead images to use. I only have 3 here because just to keep the demo project small. But ideally you would have like a 3x3 grid of beads to really sample your whole field of view to generate the model here. But you might find that you don't need that many to get good results, and so there's a little bit of kind of just experimenting there, but to be safe, you can use 3x3 grid of beads. And actually, while this is going on, so we have a little progress tracker in there. You can see we're almost done. I'm going to open up PG in the meantime to show an example of the good bead image, but okay, so let's just let it continue. So it's gonna generate that model for you, kind of show you some heat maps of what the modeled sort of displacement field or chromatic errors are that are present in your system. Those are plots that actually show how your data was corrected. Here's some CDFs that are showing a preliminary spatial analysis of your input data set. And then they all get closed, and you get some print statements here that kind of just tell you where things were saved, give you a little more information if you want to dig into the weeds. There's some useful stuff in here, but you don't really need to worry about it. And just very quickly, let's look at an example bead image. So if we go back to our project folder, our demo project folder, it looks a little different, right? So we have our input data untouched. We have that channel key I talked about. This is a table that maps bead channels to single molecule dataset channels. And if you make a mistake or need to restart there, or just want to edit it manually, delete this file, open this file, do whatever you need. So my bead images, this is where our beads were originally stored. They've been sort of moved around a little, but I do just want to show you what a good bead image looks like. So let's just look at one channel here. You can see there's like, the beads kind of span the whole field of view here, and then our Z stack also sort of spans the, kind of does a good job of spanning the focal plane of the beads. And yeah, and just, there's not too much clumping either. That's key. You kind of want to make sure you have these single beads, make it easier to localize. And yeah, so that's what that looks like. The bead analysis folder, this is kind of just like information about the modeling process. So these heat maps are kind of just like more, they're representations of the modeled chromatic error or the displacement fields generated based on the beads for each channel in your imaging system. So as you can see, moving, and the channels are indicated in the file names as well as the titles here, but you know, the function generated to go from, register 48 to our reference channel, which in this case is I5, looks quite different from that used to do 594. So there are some qualitative differences there in the data you're generating in those channels, and so it's good to reassure ourselves that we are doing some meaningful work here, standardizing our downstream analysis. These displacement TIFFs are just TIFF files. You can read details in our GitHub, but they're basically just like evaluations of the displacement models at each pixel value, if you want to do some like course correction of a pre-existing data set. And then really the most useful stuff is in the results. So this is your input data set now corrected. It's got this little new substring at the end of the file name, but same structure as your input, same units as your input, and it's just going to be those corrected coordinates for whatever you want to do next in your analysis. So these nearest neighbor CDFs, this is kind of like the preliminary analysis that the script does. So, I don't know if this is even useful to you, but if you are looking for nearest neighbors and in your between channels in your data set, here you can see for me, these were multifluorescent beads used to generate an example single molecule data set. So the true physical distance should be 0. Before BeadBuddy, we have this whole distribution out to 200, 300 nanometers. After BeadBuddy, we're down, close to like 20 nanometers 3D. So we are accounting or correcting quite a bit of error here. And these plots can sort of just give you sort of an idea of the magnitude of correction that is happening in your data set across channels. And then the CDFs are just the coordinates used to plot those CDFs. CDFs are saved as CSVs, then the fig file if that's useful for you. And then very last but not least, we have some plots that sort of just characterize how exactly your single molecule data was corrected. So each one of these points in the quiver plot or arrows corresponds to an input coordinate, and the arrow sort of shows how it was corrected based on the displacement model. And then if you have a Z, three-dimensional data set in Z here, it just shows, in the X as a function of, nanometer in the XY plane, what kind of Z correction was applied to one of your data to each coordinate in your data set. And, each data set of coordinates corresponds to a point here. So yeah, that is what happens when you run the script. And I really hope you guys found this helpful. I really hope you find some cool applications for BeadBuddy to whatever awesome single molecule imaging project you're working on. And if you have any questions or issues, please don't hesitate to reach out, leave a comment, and I'll do whatever I can to help you out. Thanks.